Zirconium errors and hazards in the nuclear industry. Part 3. Failures in parachute testing. Please note that NRC and industry records in the following presentation may contain terms that are unfamiliar to the average viewer and which are not explained or discussed in detail here. Understanding all the terms in these records and all aspects of zirconium metallurgy and nuclear technology is not necessary to recognize the serious nature of the problems described. In the interest of clarity, the focus is on straightforward statements in the records showing problems and misconduct documented in NRC and industry records that are available on the internet. Please don't get hung up if every technical detail is not perfectly clear at this point. Sources and references are listed at the end of the presentation for those who want the details and more information on these problems. Zirconium failures that led to radiation releases in the Millstone reactor in Connecticut is one of many incidents that demonstrates the importance of understanding fundamental zirconium properties when designing nuclear components. Information on the NRC website appears to indicate that at least 4 types of zirconium failures contributed to multiple fuel rod breaks. One type of failure was due to zirconium cladding creep that reduced fuel rod diameters during irradiation. Second, zirconium springs in fuel assemblies designed to hold fuel rods in place relaxed during irradiation in the core. Relaxed springs failed to hold fuel rods whose diameters were reduced by radiation. Coolant crossflow caused loose fuel rods to vibrate and spin. Third, abrasion between fuel assembly spacers and spinning fuel rods wore through zirconium. Fretting wear created cladding breaks. Cladding breaks allow radioactive isotopes to leak out of fuel rods into primary coolant water. During some nuclear accidents, primary coolant water was released into the environment, as described in NRC reports of the 3 Mile Island accident and the Fukushima accidents. Therefore, contamination of primary coolant water is a safety concern. Coolant could leak into fuel rods and corrode zirconium cladding from the inside. This 4th type of zirconium failure, corrosion, could increase radiation releases by enlarging openings and by weakening fuel rods, making them more likely to fragment. Note that all 4 of these failure modes involve zirconium texture to a greater or lesser extent. Only after millstone failures did the manufacturer fix the problems by replacing zirconium springs with a spring made of metal that did not relax as quickly when irradiated. NRC records show that over a decade earlier at Wolf Creek, the same types of zirconium failures led to 44 fuel rod failures in Westinghouse assemblies and reactors, and fragmentation during fuel handling. Abrasive wear and corrosion weakened and broke nuclear fuel rods, creating immediate reactor hazards and later waste handling hazards. It should be noted that these types of failures caused by zirconium distortions and spring relaxation, which allow fuel rods to be moved and vibrated by coolant flow and wear through zirconium cladding, were described decades before the millstone failures in the 1983 publication Creep of Zirconium Alloys in Nuclear Reactors. The 1983 publication noted that no problems of this nature had been observed for modern designs. However, later, these types of zirconium failures occurred in Areva, Westinghouse, and Siemens fuel assemblies. In 1993, one report noted that a new type of vibrational fretting is emerging, which raises the questions: do companies test new designs for known zirconium limitations before using them in reactor parts, or do they repeat mistakes and then rediscover zirconium weaknesses only after multiple failures of new designs in operating reactors? With their ignorance of fundamental zirconium properties, needlessly increasing risks to the public. In 2014, springs failed to hold fuel rods in the North Anna plant. These fuel rods were also spun by hydraulic forces. Fretting wore through the cladding, causing fuel rod breaks and releasing an estimated 15 fuel pellets into the water. about 7 fuel pellets could not be located and are believed to have disintegrated in coolant water. In the aviation industry, before new commercial aircraft or newly designed parts are deployed to the commercial sector, extreme flight testing is often done to check performance and to identify limitations. Systems and parts are often tested to failure in order to improve understanding of new designs and sometimes to check backup and emergency systems before exposing the public to hazards, especially when previous failures have exposed weaknesses. In the nuclear industry, long design and operating lifetimes required to make nuclear power profitable for owners sometimes makes such test-to-failure performance checks in dedicated test reactors impractical. Such rigorous testing of systems to determine if everything will work properly during long operating lifetimes and to verify that backup systems and other safety measures will work as intended would take too much time and cost too much. Intentional tests to failure would be too hazardous and create legal liabilities. Instead, the nuclear industry sometimes does less rigorous testing and shorter experiments with new designs and operations in commercial reactors, which can be especially risky for surrounding communities if those responsible for the nuclear industry's version of flight testing, particularly the NRC, don't seem to know which way is up sometimes because of wrong way errors and do not prevent the spread of inaccurate technical information. In the aviation industry, when new designs and poorly understood systems might cause unrecognized design or control problems that could cause aircraft crashes or use of emergency systems, flight testing is sometimes informally referred to as parachute testing. Do tests of new designs and operations in commercial reactors potentially reduce surrounding communities to parachute testers? A Nuclear Energy Agency report described how a test at the Chernobyl nuclear power plant intended to determine if core cooling can be ensured in event of loss of power and improve reactor safety systems turned into a catastrophic accident. Within hours, technical misunderstandings and incompetent information practices turned a test intended to improve safety into a nuclear accident that made surrounding communities uninhabitable. New component designs and operation procedures are sometimes tested in commercial U.S. reactors. As occurred with the spring relaxation and fretting failures, misunderstandings of fundamental zirconium properties have led to a large number of unexpected zirconium distortions, deformation, and bowing problems involving fuel rods, fuel channels, and guide tubes in operating reactors. Some redesigns are not thoroughly tested before wide use in commercial reactors. As their name implies, control rods and control blades, sometimes collectively called control rods, are relied on to control nuclear reactors. Insertion of control rods slows down the rates of nuclear reactions and reduces heat generation. When reactors malfunction, fast insertion of control rods, called scrams, shuts down the reactor quickly. While control rods are not made of zirconium, zirconium parts do help position control rods in the right positions so that they can be moved into locations required for operations in scrams. Many U.S. reactors are scrammed each year. Control rods can be thought of as the brakes of a nuclear reactor. According to an ANT report, in the decade preceding 2011, about half of U.S. boiling water reactors reported control blade interferences due to zirconium fuel channel distortions in bows. Fuel channels from major vendors were affected. Areva reported unexpectedly high fuel channel bows increased control rod friction in some U.S. reactors. Some control rods failed settle testing. Some cells were considered inoperable. Since control rods are the primary means of local reactivity control, there are strict regulations governing the ability of control rods to move freely during all anticipated operating conditions. Excessive part bows risk loss of reactivity control. Although in ASCA atom-built reactors, observed fuel channel friction was small in comparison to drive forces available to move control rods in event of scrams. More extreme zirconium fuel channel bows could cause fuel rods to stick, and significant channel bows can decrease loss of coolant accident thermal margins, reducing safety margins. Despite what this Arriva slide seems to indicate, zirconium parts just don't randomly change shape and bow. Like most material problems, bows appear to be random when causes are not understood and reactor conditions and chemistry are not adequately controlled. Many bows are caused by uneven growth, while some reversible thermal expansion in the intense heat of a nuclear core is expected. For other reasons, one side can grow longer than the other side, and a part can deform and bow irreversibly. Outward bows can be worse if ends can't move, because the ends are fixed in place when the sides grow, and when uneven thermal and pressure forces cause zirconium creep. Chemical reactions between flowing coolant and zirconium can add more hydrides or oxides faster to an upstream surface than downstream or shielded surfaces, causing uneven growth in bows. Fast neutron irradiation also causes serious bowing problems in different ways. Fast neutron collisions can knock zirconium atoms out of place. Like pool balls after a break, atoms moved by neutron collisions don't automatically resume the same close-packed positions. They move and can occupy more space or take up different positions. Zirconium can creep and grow when irradiated. When more neutron collisions move more atoms on one side of a part than on the other side, part growth is accelerated and is more uneven. Parts bow. Failure investigations of zirconium growth in bows examine chemistry, microstructure, and texture because they determine how atoms move and how parts grow. While some of the details can get complicated, some of the basics of zirconium component microstructure and texture are fairly simple. Each component is made of thousands of microscopic, irregularly shaped crystallites. Each irregularly shaped crystallite is made of thousands of atoms, most of which occur in hexagonal close-packed atomic arrangements at operating temperatures. Texture is a measure of the distribution of orientations and directions of atomic arrangements in those crystallites. And because those atomic arrangements determine where atoms knocked out of place by neutron collisions can move and settle, metallurgists have long known that irradiation growth depends on chemistry, microstructure, and texture. To put it in simple terms, growth in bows depend on what atoms are there, how they are arranged, and how they can move when interacting with other atoms and when knocked out of place by fast neutrons. The close-packed hexagonal atomic arrangements in zirconium alloys make them behave differently than more common alloys whose atoms tend to have cubic arrangements. In the more common cubic-based arrangements, higher symmetry often makes directions less important. In hexagonal close-packed atomic arrangements, properties that determine growth in their close-packed directions can be very different than properties in less densely packed directions. And if zirconium growth needs to be understood and unexpected part distortions are to be avoided, engineers must pay careful attention to how the hexagonal arrangements tend to be oriented in zirconium parts. That is, they must understand texture. To complicate matters, high temperatures that occur during some accidents cause zirconium alloy atomic arrangements to change from close-packed hexagonal arrangements to more open types of cubic arrangements. The atomic movements that occur in this hexagonal to cubic transition during some accidents can cause even greater distortions and complications. These atomic movements and distortions also depend on the texture of the zirconium alloy. Zirconium part distortions caused by the 3 Mile Island accident were far greater than those described here. Many scientific studies have established that texture and atomic arrangements cannot be neglected in designs of nuclear components that will release radiation when they break, or can interfere with control rod insertion or reactor shutdowns when they grow, bow, and distort. Despite what the NRC stated in its texture report, published studies and the experiences with control rod interferences demonstrate that inaccurate texture information can be a safety concern. Blanked out information in an AREVA report posted on the NRC website makes it difficult to see exactly why so many zirconium parts distorted and bowed, and to understand AREVA solutions to distortions and their share of control rod interference problems. Available AREVA and ANT information does indicate that in the early 2000s, new designs were introduced and fuel was taken to higher burnups. Fuel cycle lengths and power densities were increased. Higher burnups expose components to more extreme conditions with higher and more uneven neutron irradiation, causing much of the unanticipated distortion and control rod interference. The extreme reactor conditions led to complex combinations of chemistry, neutron irradiation, zirconium microstructure, and texture effects that created uneven growth and distortions in several types of zirconium components. Similar bowing involving fuel rod designs and extended burnup had been reported years earlier, suggesting repeats of earlier failures, similar to apparent repeats of failures seen in the history of zirconium spring relaxation in fretting wear. Some component bowing and distortions were described as new phenomena. A poorly understood process called shadow corrosion was believed to have induced fuel channel distortions. Shadow corrosion and bowing involve both growth from zirconium chemical uptake of hydrogen from coolant water and neutron irradiation growth. The growth is strongly influenced by the state of zirconium in reactor conditions, and the specific choices of new design and operational parameters determined how the distortions in bows developed. Therefore, the zirconium distortions and control rod interferences might be seen as the results of failed experiments with higher burnups in new designs in commercial reactors. However, experiments require accurate measurements under carefully controlled conditions. Given the NRC's history of failures to prevent the spread of inaccurate technical information in industry, particularly zirconium texture, and NRC findings that AREVA and other companies practiced poor quality control involving temperature measurements and failures to document technical justifications for design process changes. And, as described in more detail in the next section in the MOX Fuel Qualification Project, NRC spread of inaccurate information, wrong way errors, and other nonsense on zirconium microstructure and properties. These distortions and control rod interferences don't appear to be the results of experiments in any scientific sense of the word. The unexpected bowing, distortions, and control rod interferences appear to be more like the results of trial and error, hit or miss, and failing to learn from mistakes, too often repeating mistakes with reactor operations and new designs. The NRC has dismissed zirconium texture errors because they did not consider the errors to be a safety concern, and appear to have accepted industry determinations that unexpected zirconium part growth, bowing, and deformations created by misunderstandings of fundamental zirconium properties, and bowing that could lead to local excessive overheating of fuel rod cladding that may lead to failure, are not defects because, according to industry, the condition does not create a substantial safety hazard. Given that industry has recognized that zirconium fuel rod cladding is the reactor's primary safety barrier, and strict regulations govern control rod movements, the history of the reliability of NRC and industry safety determinations
is of interest. Although not initiated by zirconium failures, one notable situation was described in the report of the President's Commission on the accident at 3 Mile Island. A valve, called a pour valve, failed to close, creating a loss of coolant accident. If operators had realized that the pour valve was stuck open and taken the right actions, the accident at 3 Mile Island would have been little more than a minor inconvenience. However, years earlier, the pour valve was not designated as a safety-related item because it had a block valve behind it, and the block valve was not safety-related because it had a pour valve in front of it. The utility makes the initial determination as to which items are to be designated safety-related, subject to NRC approval. The report states that items not designated as safety-related need to not be reviewed in the licensing process and are not required to meet NRC design criteria, need not be testable, do not require redundancy, and are ordinarily not subject to NRC inspection. Independent reviews and other quality assurance measures required for safety-related systems by the NRC did not cover the PORV, so training, equipment maintenance, and operation procedures were inadequate. The report stated that as a result of these deficiencies, the safe operation of the 3 Mile Island 2 plant was impaired. Years earlier, a pour valve stuck open at another plant operating at only 9% power. The operators took improper actions, although significant core damage did not occur there. Over a year before the 3 Mile Island accident, an engineer wrote that if the event had occurred in a reactor operating at full power, it is quite possible, perhaps probable, that core uncovery and possible fuel damage would have occurred. During the 3 Mile Island accident, engineers had difficulty in analyzing events, apparently in large part because utilities were not notified of the pour valve issues and the likelihood for erroneous operator actions, which appears to be in keeping with NRC regulations because pour valves were not determined to be safety related.
NRC and industry failures to understand fundamental zirconium properties led to component designs that failed to perform properly in operating reactors and reduced accident margins. And while these problems were costly for some to fix, how profitable were these failures to those in the right positions and those in charge of the supposed nuclear renaissance announced shortly after these failures? Accurate understanding of zirconium properties should have guided testing to identify and eliminate weaknesses before parts failed in commercial operating reactors, before they created potential hazards. Misunderstandings arise from bad technical information. NRC practices like failures to pursue distribution of distorted information and failures to require reviews of suspect information leads to misunderstandings like bad designs, bad operating decisions, and failures in operating reactors. Instead of designing parts based on sound technical information, the NRC and industry are too often misled by misunderstandings and have to learn from mistakes, sometimes repeating failures. Trial and error, hit or miss, and learning from mistakes are not acceptable strategies when the wrong actions can create nuclear accidents like Chernobyl. When things go wrong for any reason, failures to understand zirconium and its high-temperature behavior and hazards misleads accident responders, as happened at Fukushima. Their failures to understand the consequences of adding seawater to hot zirconium appear to have made that ongoing accident worse. And poor understanding of zirconium can undermine lessons learned from accidents like Fukushima, possibly creating cycles of repeated mistakes. The nuclear industry uses computer code to help develop designs and guide operations. During accidents, responders rely on computer code to determine reactor conditions, to decide what they can do to control accidents, and to determine whether or not to order evacuations of surrounding communities. because fast decisions are required, and deadly radiation, extreme temperatures, and damage can make direct inspection of reactor conditions impossible. Fuel rod prediction codes, like Copernic, rely on technical information on the fundamental properties of zirconium alloys. Industry developed some of this code during the same time period as they developed and deployed designs of reactor components whose weaknesses were discovered only after component problems and failures due to fretting and part bows occurred in operating reactors. Computer programmers have a saying, garbage in, garbage out. How much of the computer code was undermined by reliance on information corrupted by distortions, wrong-way errors, and misunderstood zirconium properties? As this ARIVA slide indicates, some of these codes are used in accident analysis. As this NRC memo notes, fuel behavior during a loss of coolant accident is determined almost entirely by the cladding. So computer code that predicts zirconium behavior under never-before encountered accident conditions might be necessary to help accident responders make fast decisions. But will accident responses, misguided by unreliable computer codes, include strategies that essentially amount to hit or miss, trial and error, and learning from mistakes that cause radiation releases that can't be called back? When the next nuclear accident occurs, will surrounding communities be parachute testers for untested computer code? Does NRC approval of flawed code transfer accident liabilities to the public from companies who profit from the false assurances provided by the code based on inaccurate technical information?
How did the NRC and industry determine what components are used in commercial power reactors? Claims of proprietary information hide many of the details from the public. But after the San Onofre closure, due to concerns over other types of material failures, some of the information that shows how the NRC and industry operate became available. A request for exemptions from regulations governing acceptance criteria and evaluation models for emergency core cooling systems, and a license amendment for unrestricted uses of certain types of ARIVA fuel at San Onofre was submitted. The NRC had questions related to ARIVA fuel rod bows and requested additional information. How is the NRC staff going to use some of the information required to evaluate the request? The NRC staff intended to run FRAPCON, a computer code for the calculation of fuel rod behavior at high burnup, using, among other data, cladding texture factors. In 2016, the NRC continues the legalistic approach of regulatory exemptions instead of maintaining technically responsible regulations and information. How much of the information being evaluated for requests is accurate and relevant?
For more information on the background of this presentation, please see Part 6, Technical Qualifications and Experiences of Sources and Organizers of Zirconium Hazards in the Nuclear Industry.
Please consider asking your government officials to ensure that regulatory agencies in the nuclear industry maintain accurate information so that repeated and unnecessary failures are prevented and the right decisions are made in response to nuclear accidents.